Hi everyone, my name is Akshay Suresh. Today I'll be presenting my work on training a unit to detect Amazon rainforest cover in Sentinel-2 satellite imagery. Precise forest monitoring is essential to identify illegal deforestation activities. Satellites orbiting the Earth every day offer a convenient means for global forest monitoring. However, satellite data come with its own challenges. A single satellite can click over 1,000 images per day. An image scene may also contain over 1 million pixels, rendering manual data labeling cumbersome and expensive. Here is where artificial intelligence can advance forest mapping by enabling rapid, automated forest detection and disturbance change identification at scale. For my study, I chose the unit as my model architecture of choice. The unit is a fully convolutional neural network comprised of a contracting path called the encoder and an expanding path called the decoder. The encoder takes in an input image and downsamples it in steps to multiple spatial resolutions, thereby helping the model learn about broad-scale structure. The decoder starts off with the encoded image and upsamples it iteratively in steps back to the original image resolution, thereby helping the model pick up granular details. To train my unit, I leverage an open-source label collection released by Bragagnolo et al. 2021. This collection includes nearly 500 training images, 100 validation images, and 20 test images of the Amazon rainforest region. Each image spans 512 by 512 pixels with 10-meter spatial resolution. These images come with 4 color channels, namely red, green, blue, and near infrared. I pass the input images through my unit, and I train my model to predict binary segmentation mass as output. These mass hold ones at pixels identified to be forest and zeros elsewhere. To emphasize model performance on the foreground forest pixels, I adopted the dice loss as a loss criterion for model training. For viewers interested in further technical details, such as the different encoder architectures I trialed, the various hyperparameters I optimized for, I refer viewers to the project website and the GitHub repository. As a final outcome from my study, I present to you the performance metrics associated with my best optimized model. My best optimized model achieves a recall or true positive rate of nearly 97% on the validation and test datasets. Note that my performance metrics are very similar across the validation and test datasets, suggesting healthy generalization across the two datasets. However, my test dataset is rather small, including only 20 images. Therefore, for a more realistic test of my model performance, I encourage interested viewers to leverage my open source model weights from the Weights and Biases platform and integrate my solution into real-world deployment platforms. That way, my model can be tested on much larger datasets in practice. I present some sample code on how to integrate my solution into your custom workflows on the project website. Thank you very much for your time and attention.